Good morning, everyone. Thank you for joining. My name is Kevin Grimes. I'm with the PDS Imaging Node, and today I will be presenting cloud processing of PDS archival products with Amazon Web Services, Kubernetes, and Elasticsearch. So I'm going to begin with a quick introduction to the PDS Imaging Node, who we are and what we're all about. So we are the Cartography and Imaging Sciences node of the NASA Planetary Data System. We're home to nearly 2 petabytes of digital image archives, and we're growing rapidly. So how does our backend processing work now? How does that work? So to start, it might help to understand the front end, and for that we have the image atlas. So this is our primary tool for discovering data within our archives. It's a JavaScript web app running on premises or being served from on premises, and users who download it and access it using their web browser, they interact directly with our Apache Solr backend, which is a search platform very similar to Elasticsearch. It's built on the same underlying technology as Elasticsearch. For data access, we serve up our products over HTTPS, and you can browse this very simple HTML front end to identify which products you want to access and download. And a limitation here is that this HTML viewing that you see here on the right, that is a exact mirror of how these files exist on disk. And that can be quite limiting, as we'll discuss in a minute. And finally, for search, we have a Solr endpoint exposed to the internet. It has quite a bit of powerful functionality built in, and we've leveraged that functionality to index a diverse, create a set of diverse indexes which you can search on. Wherever you're running your software, it's really easy to interact with Apache Solr. So given all of that context, why change? What's prompting our decision to evolve? So we have some new requirements for our services, and starting with the image atlas, we need to be able to store data in multiple different data stores. So simply serving out of Apache Solr is not good enough. Additionally, we have availability issues and cumbersome upgrades. I'm not going to go into too much detail there, but due to the nature of how these applications are designed and deployed, they have availability issues, and upgrades are non-trivial, unfortunately. For data access, we store data, or we want to be able to store data on multiple different file systems, including non-traditional file systems like object stores, such as S3. That's a requirement that we have. And also, assuming that we're going to start storing data in places like S3, which charge you for each file you download, we want to make sure that we can mitigate those costs. And finally, for search, we want to make searching easier than having to learn the whole API, the Solr API, right? It's non-trivial, and we want to make that easier for users. And to make it easier also to impose structure on your search results. So instead of having just a set of collections returned by Solr, which you might not necessarily know what they mean, we want to be able to abstract that away from the user a little bit to provide a better experience. So how do we implement this? What are the solutions? So firstly, we use AWS Cloud primarily for 2 reasons. One is that they offer managed services, so you don't have to necessarily worry about provisioning virtual machines, right? You don't have to worry about spinning up Elasticsearch or spinning up Kubernetes. All that's done for you under the hood, which makes it really, really easy to do upgrades and provision things really quickly without worrying about things going wrong. Additionally, a big advantage is that you only pay for what you use, right? So instead of spending tens of thousands of dollars on servers up front, as we do currently, instead you can just pay by the hour for the servers that you are using, and no more and no less. And you can spend some of that money that you're saving instead on more interesting things like hiring more developers potentially, and more exciting efforts. So the architecture approach, the style that we're following is the microservices architecture. And for us, that effectively entails having decoupled components, so individual components which can run on their own and they can be developed on their own in isolation. But they communicate with each other using RESTful APIs. And so these individual components on their own, they're not necessarily doing too much, but when you group them all together, you can have a really powerful system. Finally, for containerization, we're deciding to containerize pretty much every aspect of our system using the Docker technology. And the reason for that is that Docker containers are very easy to scale. They spin up in a matter of seconds, and they're ephemeral also. So if one dies, if the host that your container is running on dies, it's not a problem. It'll just spin up another one elsewhere. And that orchestration is even easier to do if you're leveraging orchestration frameworks such as Kubernetes. So now getting into the architecture of the system. We're going to start with a high-level overview of the system. So this is all of the different services that we have running under the hood. But for now, we're only going to zoom in on a few of them, and starting with the imaging API there at the middle. So the imaging API is really the center or the brain or the nexus of our entire service mesh. So what is the imaging API? Well, you can think of it as a bit of a gate or a portcullis of a castle. It's the only service that lets users interact with our system. So it's the only way to get into the system. And the advantage of that is you're really able to impose authentication and authorization at a single point. You don't have to worry about requiring all the individual components of your system to have this set up. You can just impose it at the entry point and count on and determine at that point what roles a given user has, if any, and then pass that along into the rest of the system. The imaging API is a very simple web app. It's defined by the Open API 3.0 standard. And the internals of it, and so a great perk of this is that the internals of the API service mesh can change without impacting user syntax. So to kind of explain what that means, I have this class diagram here, and you can see the API service up at the top. And so suppose a user sends a request saying they want to search for something, right? So the API service is going to do A and A, it's going to parse their input, it's going to scrub their input, and once it's kind of determined that the user is able to do this thing and it's determined what it is that they want to do, it's going to use the service router, which is going to route it to the appropriate service that's running inside of our mesh. So the user doesn't necessarily have to know the details about how that application is being invoked. That's all handled under the hood, and we can change how that application is handled under the hood because the user is not interacting with it directly, it's interacting with the imaging API, which then proxies it to the appropriate service. Next, we're going to talk about the data access API. So the motivation for this is, as I mentioned, we have data stored not only on premises at JPL, but also at other data nodes. So for example, USGS, and also in Amazon S3. And the problem, or one of the problems, is that we need a way for users to not necessarily know that data is being stored in this S3 bucket or that S3 bucket or at this server at JPL or all of that. They don't really care necessarily, but we need to be able to support having data in these different locations without confusing the user. And also another really big requirement is we need to be able to manage egress costs, aka taxpayer money, since we're federally funded. And the way we do that is with user access control, which helps to ensure that legitimate users of the system are able to access the data without a problem. However, users who might try to abuse the system will have their access throttled or revoked altogether. And we'll talk about how we have that deployed. Next is the search API. So the way we have our system architected is we have multiple different search indexes breaking up our data logically. For example, we have data, our indexes for our PDS3 products, we have data for our PDS4 products, we have indexes exclusively for Elasticsearch, we have indexes for machine learning metadata, and the point of the search API is to take all those different indexes, of which there's many, and abstract them away using a simple to use API. So users don't necessarily have to know which index they need to hit. They just need to know what they're looking for. Finally, I'm going to talk briefly about a use case that we have, which is the image atlas and how it interacts with the Imaging Node API. So on the right here, we have the entirety of the image atlas's architecture, but for the purposes of this discussion, I'm going to zoom in on specifically the querying capability. And so the way that works, on the right here, we have the Atlas front end, and you can imagine a user maybe making a search for insight data, right? So they make that search in the Atlas, and the Atlas then queries the Imaging Node API, which accordingly routes to the Search API, and which then in turn queries the appropriate Elasticsearch index for that insight data, and then serves that back up to the user so that the user is able to find the products that they need. All right, now I'm going to talk briefly about how all of this is deployed, starting with the Imaging Node API. So we use CloudFront, which is a Amazon offering which lets you do per request caching, and it actually does caching on based on where in the world your request is coming. So if you have a request coming from East Asia, it will create a cache in that region, and East Asian requests will continue to hit that cache instead of going all the way to where our servers are running in Oregon. We also use WAF, which prevents application abuse. And so one of the offerings that one of the things that it does is it lets you throttle user access if needed, and it's a really handy tool. It stands for Web Application Firewall, and so it prevents users from abusing the system. Also, we have API gateway set up. It routes requests to the appropriate service under the hood, like I mentioned. And finally, we also use Amazon Cognito, which integrates with different identity providers like JPL LDAP, which we use, or you can also use Google and Facebook OAuth for authentication and authorization. Lots of different options. Here's a diagram describing what I just showed. At the bottom, you see 3 different regions, could be anywhere in the world. And then at the top, we have our services running in Oregon. So you can imagine users, going and hitting Oregon, and that can take a while, but every request that they make can get cached, and so subsequent requests for the same thing will get cached. It'll be much, much quicker for the end user. Next, talking about the data access API. So the use case here for CloudFront is actually very similar to the previous one, with the difference that instead of caching requests, API requests, we're actually caching the data products themselves. We also use the Web Application Firewall for this purpose, and we point to S3 and BGFS storage, and API Gateway for routing. So we route our user requests using API Gateway. So as an example, suppose that a user queries the imaging API for a photo from Mars 2020's entry, descent, and landing. Then the imaging API, or data access API, is smart enough to know that that data is in an S3 bucket, so it gets that URL and sends it to the user. And then the user can then follow that redirect and download the product. For the search API, we use CloudFront, again, for request caching, and API Gateway for routing to Elasticsearch indexes. We also take advantage of managed Elasticsearch. And like I mentioned earlier, it's really handy for upgrades and maintenance. Finally, for the Image Atlas client, it's a React.js application built into a Docker image, which is in turn wrapped in a Kubernetes deployment. And some of the state that the Image Atlas needs is stored in a CMS using the Strapi technology. It queries the search API under the hood for image products to render. And Kubernetes manifests are all packaged as a Helm chart, which we'll see in a second, and is deployed using AWS's Elastic Kubernetes Service, or EKS, which is their managed Elasticsearch offering. So now here, there's a lot going on here, but you can see there's 2 separate deployments, one on the left and one on the right. One is for, on the left, is for the Atlas front end, and the one on the right is for the Atlas CMS, or the back end. And there's replication happening here, courtesy of Kubernetes, so that if one of these containers goes down, another one spins up, no problem, and the user's access isn't affected. And there's interactions with the search API and with the CMS database happening, and all of that access to these two services is handled by an ingress, which is linked with Amazon's Elastic Load Balancing. So all of that is integrated into the rest of Amazon's ecosystem. So in conclusion, there are a few different things. So for one, microservice architectures enable diverse applications to interact with each other and form a complete system. Also, cloud computing is entirely feasible for data archival workloads. Serving data from the cloud can be cost efficient if the proper safeguards are put in place. For future work, one of the big things we want to do is we want to integrate with the PDS API being developed by Engineering Node. This is an ambitious effort that they've undertaken to effectively unify all the different nodes, all the different discipline nodes and their APIs into a single location. It's a great thing, and the way we've interacted with this, or the way we've designed this, is we should be able to interact with them no problem. Additionally, we hope to develop SDKs to interact with various API features. Think about a Python library that does searching for you, searching against our indexes, or a Go module which you can put in your code to download data products. And there's additional API work that we hope to do, including bulk downloads and metrics. So there's still work to be done for sure. All right, and with that, I'll put up my references, and if anyone has any questions, I'd be more than happy to take them. Thank you.